All right, we're going to take another look at probability in this section. And in the last time we looked at it, we introduced these basic ideas of probability, but one important thing that we did was that we assumed that all outcomes of an experiment be equally likely. That's actually not necessary assumption, and we're going to drop that assumption in this section and just develop a more general approach. So probability really is a function. And it's a function whose domain is a sample space, right? A set of possible outcomes. And it's a function that maps an event to the set 0 to 1 in the reals, right? It assigns a probability, which we know has to be between 0 and 1. And it has the following properties. So it's a function. It has these following properties that for any event in the sample space, A, the probability of A is greater than or equal to 0. The probability of the whole sample space is 1, and we've actually already seen, kind of outlined why those are true. And if, and this is part of the definition, if A and B are subsets of S, so if A and B are mutually exclusive events, then the probability of A union B is the probability of A plus the probability of B. It's part of the definition, but it seems like an obvious an obvious thing to include, because if the events don't overlap at all, we should be able to find the probability of the union by adding those probabilities. Next, we've got this theorem with some results that we've already done, and these proofs will be the same as the ones that we've done. So we're not going to reprove anything. But if A is an event and A complement, A prime is the complement of A, then the probability of A complement is 1 minus the probability of A. The probability of the empty set is 0. For any event, the probability of A has to be between 0 and 1. That's pretty, I think, clear, but also it comes kind of directly from this definition in that it's a function that maps from S to the set 0 to 1, right? So that's kind of pretty, follows directly from that definition. And then the last one, if A is a subset of B, then the probability of A is less than or equal to the probability of B. So if A is an event that's sort of included in this larger set of outcomes in B, then the probability of A, the probability of that narrower defined event, will be less than or equal to the probability of B. Theorem 318, we already proved that the probability of A union B, the general addition rule, is the probability of A plus the probability of B minus the probability of their intersection. So here we do not need A and B to be mutually exclusive. And then in Theorem 319, this just extends Theorem 318, or actually, hold on, it extends this idea of if we have mutually exclusive events, which is part of the definition. If we have two events that are mutually exclusive, the probability of their union is the sum of the probabilities. So we can extend that to any number of events that are pairwise disjoint. So this pairwise disjoint means that no two sets overlap, meaning that the that for any two of these A sub i's you pick, their intersection is empty. So we would say like AI intersect AJ is empty for all A not equal to J. So if there's no overlapping at all, then the probability of the union of all of them is just the sum of all the probabilities. We're not going to prove this, but you could. This can be proven using induction. If you have an interest in that, give it a go. If you have a question about it, feel free to reach out, or if you have a go at it and want me to take a look at what you wrote, I'm happy to do that. In fact, maybe it'll make an appearance on an assignment or something. All right, so our next concept here is that of conditional probability. So the probability of B given A is denoted by this notation here, this little vertical line. This is read given that. given or given that or knowing that. It's basically saying what's the probability of some event B happens given that if we know that A has already happened. And so the probability is defined in this way, that the probability of B given A is equal to the probability of their intersection divided by the probability of A. Now, this is sort of an intuitive way to define it, because what a conditional probability does, I'm going to make some notes up here in the margin. What a conditional probability does is it narrows your sample space. So let's say I'm going to use a Venn diagram. Let's say here's my sample space S, right? There's the universe of all possible outcomes. I've got some event A here and some other event B here. And I want to know what is the probability of B given that A has already occurred. So if we know that A has already occurred, what we're doing is we're saying that this is our new universe, right? We're making the universe smaller. Kind of shrinking the sample space. So now, if A is the only set that exists, because we know that A has already happened, what's the probability that B has happened? That means we're only, if we know we're in A, then the only way we're in B is if we're actually in the intersection. So we find the probability of B, given that A occurs, by taking that intersection and then dividing it by our sample space, which now is just the smaller set A. As a quick example, suppose I'm looking at, or I'm working with a deck of cards, like a standard deck of playing cards with 52 cards, right? The probability, let's say I just draw one card, right? Let's say I want to know what's the probability that the card I draw is a diamond. Well, there are 13 diamonds in a deck out of 52 cards, and that's 1 out of 4. So there's that. But now, what if I drew the card, and before I ask you what the probability is that I got a diamond, I tell you ahead of time, hey, the card I drew is red. Now, what is the probability that it's a diamond? You would, I think, adjust your answer, because if I know it's red, there are 26 red cards, right? Half the deck is red, and all diamonds are red. So those 13 diamonds, now I'm only dividing by the probability that I got a red, or in this case, just we're doing it with straight numbers, like the number of red cards, and this probability is 1/2. So we're going to do another example, working with conditional probability, again with a deck of cards, and we're going to do a couple things. So first, imagine that I draw a card from this deck of 52 cards, and then I replace that card and I draw another. So in this scenario, I'm drawing 2 cards, but I'm replacing the first card first, before I draw the second card. So what's the probability that both cards are spades? All right, well, let's let A be the event that the first card is a spade. And we'll let B be the event that the second card is a spade. Now, the probability that they're both spades, what we want is P of A intersect B. Now, the way that we're going to find that, we want the probability of this intersection. So I'm going to go up here, and I'm going to take this equation, this is the definition of P of B given A. If we multiply both sides of this equation by P of A, we find now that P of B intersect A is equal to P of A times P of B given A. Now, depending on which conditional probability we have and how you label events, you might also write this as P of B times P of A given B, just sort of reversing the roles of those two events. But this is the basic idea here. So we're going to use this equation. This is P of A multiplied by P of B given A. All right, well, P of A, probability that the first card is a spade, that is 1 out of 4, right? There are 13 spades out of 52, so that is 1 out of 4. the probability of B given A. So assume that the first card I drew is a spade. And now I'm going to put that back and I'm going to draw another card. The probability is not going to change. I still have that same, because I put that card back, I still have that same probability that of 1/4 that I'm going to get a spade on the second go around. So now the probability, I'm going to use both of these here, both of these values. Probability of A is 1/4, probability of B given A is 1/4, and that gives us 1 out of 16. Now let's change the question just slightly. Same scenario, I draw a card, I put the card back, I draw another card. I'm going to leave A and B, these events defined in the same way. And this time we want to know what's the probability that at least one is a spade. Well, if I want the probability that at least one is a spade, I want the probability of A union B. And we know that this is P of A plus P of B minus P of A given A, minus P of A intersect B. I have to subtract off that intersection. A and B are not mutually exclusive. They can certainly both happen at the same time. So now I'm gonna, I've already calculated everything we need. 1/4 plus 1/4 minus this value we found before, 1 out of 16. And let's see, that's 7 out of 16. Okay, let's do another one. Same scenario, right? We're going to stick with this deck of cards and we're going to talk about drawing a spade. And I'm going to define these events the same way, right? So A is still the event that the first card is a spade. And B is still the event that the second card is a spade. But this is the same question. We're actually going to answer both parts A and B. But this time we do not replace the card. We're drawing without replacement. So in part A, the probability of A intersect B is P of A times P of B given A. Now the probability, the first card being a spade, that probability is 1 out of 4. But now since I don't replace the card before I draw another one, that changes this probability here, the probability of B given A. So let's suppose I draw a spade. And once I've drawn that spade, now there are only 51 cards left in the deck. And there are only 12 spades left, right? Because I drew a spade. So now this is the product we're going to find. We're going to, let's see, reduce. 4 goes into 12 3 times. 3 goes into 51 17 times. So we get 1 out of 17. So now there's the probability of A intersect B. In part B, we want to find the probability of A union B. This is still P of A plus P of B minus P of A intersect B. Now two of these values we have. We know that P of A is 1/4. We know the intersection, we just found that. That's minus 1 out of 17. But this, P of B, we're not sure, right? So look, that B is the event that the second card is a spade. Now, whether or not, the probability of whether that second card is a spade will change depending on whether that first card was a spade or not, right? So there's two ways. We have to understand that there are two ways that B can happen. I can either draw a spade after having drawn a spade for the first time, or I can draw a spade after having drawn a card that's not a spade the first time. So to find that, I'm going to kind of set this up for ourselves, kind of trying to partition B into the two possible ways that B happens. So either B happens after I get a spade first, And in that case, we're looking at the probability of A intersect B, which we already know, right? That's what we found is 1 out of 17. Or it could be the probability that I draw a spade second after I don't get a spade the first time. So we'll note that we've kind of split up B, partitioned B into two disjoint possibilities, which is why I can just add those probabilities together. I know the first one is 1 out of 17. The second one, using that theorem or that definition up here from which we derived, from which we derived this equation up here at the top. I'm just going to use that same equation, but this time using the events A complement and B, and this will be the probability of A complement times the probability of B given A complement. And we could put this together. So, probability of A complement. The probability that I don't get a spade, well, that's 3 out of 4, right? Don't get a spade on the first card that I draw. The probability that I do get a spade, the second card I draw, well, there are 51 cards left in the deck because I drew a spade, but this time I didn't draw a spade on the first one, so all 13 spades are still in the deck. So we're going to find this product. Let's see, 3 goes into 51 17 times. So we have 13 on top, and then 4 times 17 on the bottom. Let's see, this first fraction needs a 4. So 13 plus 4 on top is 17. 17 times 4 is 68. And that is exactly 1/4. So the probability that I got a spade on that second card is still 1/4. And now we can do this arithmetic. So 1/4 plus 1/4 is 1/2. 1/2 minus 1 out of 17. We get 15 out of 34. So the probability that I get at least one spade is 15 out of 34. All right, let's continue with the cards. So this time we're going to draw 6 cards in succession without replacement, so we're not putting them back. So each card I draw, reduces the number of cards in the deck by 1 and kind of reduces the pool of cards available for the next card that we draw. And we want the probability that the 6th card, right, that last card that we draw, is the 3rd spade exactly. So we're kind of interested in the situation where I get exactly 3 spades, but I get that last spade, that 3rd spade, on the last card. So let's split this up into a couple of events. Let's define the event A to be the scenario where we get exactly 2 spades in the first 5 cards. And we'll let B be the event that the 6th card is a spade. And with these events defined in this way, what we want is the probability of A intersect B. We want both A and B to happen. So this is what we're looking for. And we know that we can find the probability of the intersection by taking the probability of A and multiplying it by the probability of B given that A has occurred. So let's think about how we find. So we've basically broken this problem down into two smaller problems. The probability of B given A is actually fairly simple. So we imagine that I got exactly 2 spades in the first 5 cards. So I've drawn 5 cards out of the deck, which means there's 47 cards left. And I got exactly 2 spades, which means that there are 11 spades left in the deck. So that last probability is not too difficult. We're going to work a little bit to figure out the probability of A. So let's talk about the event A. The sample space for this event, I'll call it S sub A, is all the ways I can draw 5 cards from 52 cards. And we're pretty familiar with this, right? This is 52, choose 5. Now the number of ways that A can happen. I want to get exactly 2 spades in those first 5 cards. So how many ways can I grab 2 spades? Well, I'm grabbing 2 spades, and I need them to come from the 13 spades that are in the deck. So 13 choose 2 is just the number of ways to get 2 spades out of 13. But that doesn't account for all 5 cards that I'm drawing. So I need to multiply by this. And on top of getting exactly 2 spades, I need to get 3 cards that are not spades. So I'm going to choose 3 more cards. They have to come from, let's see, 52 minus 13 is 39. So the 39 spades that are not cards. And that means that P of A is equal to 13 choose 2 times 39 choose 3 divided by 52 choose 5. And this is the probability of A that we're going to use up here. 13 choose 2 times 39 choose 3 divided by 52 choose 5. And I'm just going to throw this all in the calculator and see what we get. So 13 math probability option 3, 13 choose 2 times 39 choose 3 divided by 52 choose 5. And then we're going to multiply that by 11 over 47. And we get 0.0642 approximately. Which the calculator, I know it is absolutely rational because each of these combinations gives you some integer, but it must be so far before it starts repeating itself that the calculator is having a hard time deciding what fraction it's equal to. So I'll just leave it in that approximation. Okay, so now that we know about conditional probability, we can talk about whether or not events are independent. So we say that the event B is independent of the event A if the probability of B given A is equal to the probability of B. This is sort of like saying that the event B, it doesn't matter whether or not A happens, the probability, the likelihood that B happens remains the same. And if B and A are independent events, then that product that we find, I'm going to scroll back up here just to look at it one more time. So this equation here at the top, right, that we've used a few times now, that we got from using the conditional probability, really just boils down to saying we can multiply the 2 events together, or the probabilities of the 2 events together. So we're going to prove this using that, right? So we know that the probability of A intersect B is equal to the probability of A multiplied by the probability of B given A, right? This is true for all events regardless of independence. But if we know that A and B are independent, then the probability of B given A is equal to the probability of B. So we're just going to make this substitution. We get P of A times P of B. So there's a really short and sweet proof of this equation. It's important to note that this is only if A and B are independent. So there's a couple ways that we use this. Sometimes we might see if this equation holds to determine if events are independent. Or if we know ahead of time that events are independent, then we know that this equation is true and we can use it. In example 342, it says, suppose a coin is tossed 10 times. Let A be the event that the coin comes up heads the first 9 times, and let B be the event that the 10th coin comes up heads. We're going to show that B is independent of A. Now, I think that the fact that coin tosses are independent of each other is something we take for granted. And, if we're working on a problem, I think we would generally just use the fact that we know that they're independent. But we're specifically being asked to show that B is independent of A, right? Coins do not have memory, right? That the coin doesn't remember whether or not the first tosses came up heads or not. So kind of our intuition tells us that they should be independent. We're going to show it. So we will show that that P of B given A is equal to P of B. Well, the probability of B given A we know is equal to the probability of A intersect B divided by the probability of A. So let's think about the event A, right? The event A is that the coin comes up heads the first 9 times. So like that I toss a coin 9 times and it comes up heads every single time. So if we think about the event A, the sample space for that event, the size, is 2 to the 9th, right? I'm tossing a coin 9 times. There's 2 outcomes each time. The multiplication counting principle tells us that that sample space has size 2 to the 9th. The number of ways A can happen is just, there's only one way it can happen. They all have to be heads. So the probability of A is 1 over 2 to the 9th. Now the probability of A intersect B is also pretty simple because A intersect B is the event that we get 10 heads in a row. Right? It's the event that I get heads 9 times and then I get heads again. So taking them all together, that's 10 heads in a row. And for the same reason that when we found out the probability of A is 1 over 2 to the 9th, we know this is going to be 1 over 2 to the 10th. Using these values over here on the left now, the probability of A intersect B is 1 over 2 to the 10th. I'm dividing that by 1 over 2 to the 9th. So this is 1 over 2 to the 10th times 2 to the 9th over 1. We do some canceling and we get 1/2. This is the probability of B given A, which is equal to the probability of B if I just consider that one coin tossed, that 10th coin that's tossed should have a 1/2 probability, and that's what we find. So we find that A and B are independent. So let's keep talking about tossing a coin. When we toss a coin, there are 2 possibilities, heads and tails. Right? So let's suppose, again, we toss a coin 10 times and we want to find the probability that we get exactly 3 heads. Right? So let's think about one way to get 3 heads exactly. One way this might happen. It's not the only way, but we're just looking at one possibility. is if I get 3 heads right off the bat and then 7 tails. Right? So now the probability that the first 3 are heads. Now we're going to use the fact that tossing coins, flipping coins are independent. We know they're independent events, which means that the probability that I get this sequence of outcomes when I toss the coin 10 times is 1/2 times 1/2 times 1/2, right? This is just, all of these have a probability of 1/2. Now, I'm going to write it out in what might seem like an inefficient way, but the way that I'm going to think of this is the number of ways to get 3 heads first. So that's 1/2 times 1/2 times 1/2 is 1/2 cubed. And then I'm going to multiply that by the number of ways to get 7 tails right after. And that's also 1/2. You might ask, why am I not just calling it 1/2 to the 10th? And we'll see why in a moment. But I'm trying to kind of separate out the heads events from the tails events in this calculation. Now, this isn't the only way to get, exactly 3 heads. This is the way it happens if the first 3 are heads. But maybe the heads that I get are here, here, and here. Or maybe the heads I get are here, here, and here, and the rest are tails, right? So there's all these different ways that those 3 heads could be distributed among those 10 outcomes. So I want to account for that. No matter where those heads lie, the probability of each of those individual ways to get 3 heads is still going to be 1/2 to the 3rd times 1/2 to the 7th, right? Because they're still independent events, and I'm still just going to multiply their probabilities together. So the way we account for all those different ways I could have the 3 heads happen in the 10 outcomes is to count them up. So the number of ways to get 3 heads is 10 choose 3, right? Of the 10 outcomes, I'm picking which 3 of them are going to be the heads. So now each of these 10 choose 3 ways to get 3 heads has this probability, the 1/2 cubed times 1/2 to the 7th. So the probability of getting exactly 3 heads is 10 choose 3 times 1/2 cubed times 1/2 to the 7th. Right, each of these has an equal probability of 1/2 cubed times 1/2 to the 7th. So I'm just going to add them all up, which means I'm adding it up 10 choose 3 times. 10 choose 3 is 120. Now 1/2 cubed times 1/2 to the 7th is 1/2 to the 10th, and that's 1 over 1024. So we have 120 over 1024, which we can approximate .1172. Now, in this scenario, where we were kind of doing the same thing over and over again, in this case, tossing a coin, and each of these events, each time we did it, was independent of the last time, right? So the probability, I split it up into 2 possible outcomes, in this case heads or tails, and the probability is always 1/2 each time. This is an example of what we call a binomial probability experiment, where we have repeated trials, each with the same probability, and we always split it up into 2 outcomes, one that we call success and one that we call failure. This kind of experiment has what we call a binomial distribution, and we call it binomial because each of the probabilities has the probability that n takes on, or that we have so many successes. In this case, in the one we just did, we were looking at the probability that we got exactly 3 heads. So we might say getting heads is a success and getting tails is a failure in that scenario. We find the probabilities that we have so many successes by computing this, and we saw this happen right up here. right? This was that same calculation. And we've seen this calculation before. If I add them all up, this is how the binomial distribution or the binomial expansion works that we saw back in, I think it was section 3 when we were first looking at permutations and combinations. So using the language of theorem 3.21, in this example, we would say that a success would be getting heads and failure is tails. In this case, P is always, always, always the probability of success. So P is equal to 1/2, and in this case, Q is always the probability of failure. This is equal to 1/2 also. They're not always going to be equal just because they happen to be, because we're just looking at the scenario where we are tossing coins. And we were tossing a coin 10 times, so that means N is equal to 10. It is always the case that P and Q have to add up to 1. Because you're basically partitioning the set of outcomes into a success and failure. So this particular thing happens or it doesn't. So I either get heads or I don't get heads. In any scenario, you can always kind of do that. You can break it down into a success and failure. With tossing a coin, it's pretty obvious, right, that we get 2 outcomes. But if I think about the scenario where we were drawing cards and I was counting spades, you know, maybe it's possible I might count success as getting a spade, and I don't have to think of the other outcomes as, oh, this suit, or this other suit. I can just say failure is not getting a spade. Right, so you can always kind of partition into 2 outcomes, two classes of outcome to define your success and failure. What is absolutely a must is that these are repeated experiments that are independent. So we have n independent trials. We call them Bernoulli trials, but the idea is I'm doing the same thing over and over again with the same probabilities each time. All right, so let's do another one. Let's say we roll a die 10 times. So it's a fair die, a regular 6-sided die. And we want to know what's the probability of getting a 6 exactly 3 times. So we're doing the same thing over and over again. Rolling a die is independent each roll because dice do not have memory. So let's say we're interested in getting a 6, right, exactly 3 times. So let's say our success, we'll define that as getting a 6. And a failure as any other outcome. So note that we're either going to have success or failure, right? I'm either going to get a 6 or I'm not. The probability of success is 1 out of 6. The probability of failure, Q, is 5 out of 6. We'll note that these add up to 1, which has to be the case. And we are rolling this die 10 times, so N is 10. There are 10 trials. Now, we want exactly 3 6s. So we're going to use the formula. First, I'm just going to write it out. N choose K, P to the K, Q to the N minus K. So exactly 3 6s means that I'm looking for the scenario where K is equal to 3. So, and this calculation right here gives us the probability of having K successes out of N trials. So this will be N choose 3 times P is 1/6, so 1/6 to the 3rd, and then 5/6 to the 7th. And I wrote N choose 3, but of course we know that N is 10, so let me replace that with 10. 10 choose 3 is again 120 times 1/6 to the 3rd times 5/6 to the 7th. I'm just going to throw this in the calculator. and I get 0.1550. And there's our probability that we get exactly 3 6s. Okay, so now consider this. Suppose that for a given sample space, there's some experiment with some sample space, and for each outcome, I associate with that outcome some number. Now, we've done that already in that the number we associate it with is just the probability, and we can compute the probability of each outcome. But suppose that we also associate it with some separate number. For example, maybe I roll a pair of dice. I might associate the individual outcome with just the sum of the 2 dice. Maybe if I toss a coin 20 times, right, if that's my single experiment where I do that 20 times, I might, each outcome, I might just count how many heads come up. When we do this, when we associate with each outcome some other value, we call that number a random variable. So a random variable is a function, first of all, and it's a function from a sample space to the real numbers, where we define it in some way. Or we define, whatever that should be, whether it's counting number of heads or adding a number of dice, or adding the number of pips that come up on a pair of dice when we roll it. Maybe it's winnings when we, play, a game of chance, right? We might associate an outcome with a certain number of winnings or losses, I suppose. It is interesting sometimes to note that a random variable is neither random nor a variable. It's not a variable, it's a function. And it's not random. They're assigned in a very kind of definite way. We know what a random variable is going to take on for a given outcome. So now what we can do is, for a given sample space, determine the probability that a random variable takes on some specific value. And in fact, we kind of did that up here, right? We could have, in this scenario, we roll a die 10 times. We found the probability that we got exactly 3 6s. So maybe in a scenario where an experiment is I roll a die 10 times, I might define the random variable be, how many heads, count how many heads come up. And in this scenario, we, found the probability that that random variable equals 3, right? That we got 3 6s. So in this, in our next definition, if we have a random variable defined on some outcomes that occur with respective probabilities, so x1, the probability of x1 is p1, and the probability of x2 is p2. Then the expected value of that random variable, which we're calling r, is given by this sum. So this is the expected value, the mathematical expectation, also called the mean of r, of the random variable. So we can find the expected value by taking the random variable, the value that the random variable takes on for each outcome, multiplying it by the probability of that outcome, and then adding them all up. So let's do an example. Let's suppose we have a game where we roll a die and we receive the dollar value of the outcome of the roll. So if you roll a 5, you get $5. How much should you expect to pay to play the game? Or in other words, what is a fair price to pay for playing the game? And what we mean by fair price is that neither the house nor the player has the edge. That if you did it over and over and over again, you would just come out even. So if we want to know what is a fair price, or how much should you expect to play, or expect to pay in order to play the game, we want to find the expected value of the random variable, meaning over time, what is the average amount we would expect to win on each game. So let's define the random variable. We'll call it R of x, which is just the amount won on a roll. And if the outcome of that roll is x, then R of x is just x dollars. So I'm going to make a little table to organize. The outcomes, the individual outcomes that we're calling x here, are either going to arrange from 1 through 6, right? 1, 2, 3, 4, 5, 6. And the random variable takes on a value equal to x, right? So the way we've defined the random variable is quite simple. Now the probability of x, the probability of each outcome, is 1 out of 6. And what we want to find is the expected value of the random variable, which is the sum of the R of x times P of x values, according to the formula in the definition up top here. So I'm going to let x range through all the values from 1 to 6. I'm going to compute the product, R of x times P of x. So I'm going to put that in the last column here. And I'm just going to multiply. So 1 times 1 out of 6, 2 times 1 out of 6, right? I'm going to put that over here. So we get 1 out of 6, 2 out of 6, or 1/3. 3 times 1 out of 6 is 1/2. 4 times 1/6 is 2/3. 5 times 1/6 is 5/6. 6 times 1/6 is 1. And so now we're going to add these up. Okay, so I think we can, we could open up the calculator, but I think there's kind of a simple way to do this. Excuse me. Let's see, 1/6 and 5/6, that's 1. 1/3 and 2/3, that's 1. Obviously we have a 1 here, so that's 3 so far, plus 1/2. So we should get 350. That is the expected value of R, meaning, so there's no one game in which I'm going to actually get 350, right? I'm either going to get $1 or $3 or $6 or $4, but over time, if I just play it over and over again, the average winnings will be 350 on each game, and so that means that 350 is the fair price to play the game. Okay, let's do another one. Consider roulette. Roulette is a game where you're spinning a wheel and the sort of ball bounces from spot to spot. And on this roulette wheel, there's different spots where the ball might land from 0 through 36. So we'll note that 0 through 36 is 37 spaces, right? 37 spots for the ball to land. Right, and you place a bet based on, where you think the ball might land. They're equally spaced slots, so that means that there's an equal chance that the ball will fall on any particular location. So in this game, the player pays $1 and picks a number. If she wins, she'll get $36, and if she loses, she gets nothing. So we're going to let R1 be the random variable that is the amount the player receives, which means that player is going to get $36 or $0. So R1 of a win is 36, and R1 of a loss is 0. We want the expected value, which is the sum of the products R1 of x times P of x. Now, there are 37 spaces, but I don't need to think about these 37 different outcomes because I can kind of group them into two in order to do this most efficiently. So I can just group them into the event that I win and the event that I don't win, that I lose. So the probability of a win, there's only one way to win, it's got to land on the one space I picked. And so that's 1 out of 37. And the probability of a loss is that it lands anywhere else. So that's 1 out of 30, that's 36 out of 37. So now I'm going to take the value of the random variable times its probability. So the random variable of a win times its probability is 36 times 1 out of 37. And I'm going to add it to the probability of a loss times that probability, the random variable value R1 of a loss times its probability. So that's 0 times 36 out of 37. This will just give me 36 out of 37, which is approximately, we're talking about money here, so I'm going to get an approximation, 0.973. So a little over 97 cents is the expected value of R1 over time. So this answers the question of what the expected value is. However, we should keep in mind she paid $1 to play. So overall, she's going to expect to lose about 2.7 cents each play. Now let's consider the same scenario. We're still looking at this roulette wheel. She still pays $1 and picks a number, but we're just going to define the random variable differently, and we're going to let R2 be the amount that the player wins or loses, like the net amount. So we're going to account right in the beginning for the fact that she pays $1. So if she wins, her net gain now is 35, right? We're already accounting for the fact that she paid $1. And if she loses, R2 takes on the value of -1, right? She gets nothing, but she paid $1. The probabilities are the same. Probability of a win is still 1 out of 37. The probability of a loss is still 36 out of 37. So now the expected value of R2 is the sum R2 of x times P of x. So that is 35 times 1 out of 37 plus -1 times 36 out of 37. So 35 out of 37 minus 36 out of 37 is -1 out of 37, which is approximately a -0.027. So this already accounts for the fact that she paid $1, and we get that same overall interpretation that we got from the last one. So we define the random variable differently, right? In the last one, then we had to account afterward for the fact that she paid $1 to pay. And once we did that, we kind of came to the conclusion that that meant that she actually lost money each time. Here, since we're accounting for the fact that she paid $1 in the first place, right away without any additional analysis, we know that she can expect to lose about 2.7 cents per play. All right, so now we spent some time before talking about the binomial probability distribution. So in a binomial probability experiment, again, remember that means there are n independent trials, each having two outcomes. We define them as success and failure that have probability of p and probability of q, which is 1 minus p. If we let the random variable r represent the number of successes, this is absolutely crucial. In a binomial experiment, binomial probability experiment, you always want to let R just count the number of successes out of n trials. And if you do that, then the expected value of R is just n times p. You don't actually have to calculate. Now you can go through and calculate the value of the random variable times the probability and add them all up like we did in the last examples. But if your random variable just counts the number of successes, that will always just be equal to n times p. So when you have a binomial probability experiment, I guess the first step is recognizing when you have one. Because if you know it's binomial, then your calculations are a little easier. So let's say we toss a coin 20 times. Now those are independent tosses, right? Coins don't have memory. So we have 20 independent trials. The player receives $1 for each head that comes up, so we should let our random variable count the number of heads. That's our success. Our value of n is 20, because we're doing this 20 times. Now we're tossing a coin, so success and failure have equal probability of 1/2. And our random variable R is counting the number of heads, so the expected value of R is n times p, so that's 20 times 1/2, and that's 10. And what's a fair price to play the game? You got $1 for each head, so that if R is counting the number of heads, that's counting how many dollars you get when you toss the coin 20 times. So that means that $10 is the fair price to play. All right, so now some more results. Theorem 323 says we have a couple of random variables defined on a shared set of outcomes. So, you know, the roulette problem, we defined the random variables R1 and R2, but they were still on the same set of outcomes, right, where that ball would land on the roulette wheel. So if we have a couple of random variables, here we're calling them R and S, on these outcomes that each have their respective probabilities. So the probability of x1 is p1 and the probability of x2 is p2. And c is a constant. Then the expected value of c times r is c times the expected value of r. We can pull a constant multiple out of that expected value function. The expected value of a constant is just a constant. And the expected value of r plus s is the expected value of r plus the expected value of s. We can split up this function over addition. Okay, so now let's say we have a random variable, a couple of definitions. One we've already seen. The mean, which we're calling mu, of a random variable is the expected value of r. I've already mentioned that. And then the variance, which we're calling sigma squared, of a random variable is the expected value of r minus mu squared, which is the same thing as the expected value of r minus the expected value of r minus the expected value of r squared. So here we're just replacing mu with the expected value of r. So there are two different ways to write that. So we say that the variance is sigma squared. That might beg the question, what is sigma? And if you've taken statistics or have an interest in statistics or done any statistics, you may have come across sigma before. Sigma is the standard deviation of a distribution. All right, so we're going to prove this result. For a random variable r, the variance, sigma squared, is equal to the expected value of r squared minus mu squared. So we're going to start with the definition, right? We already know from the definition that on the previous page that sigma squared is the expected value of r minus mu squared. This is by definition. I'm going to do some algebra. Let's FOIL out the r minus mu squared. This is the expected value of r squared minus 2r mu plus mu squared. Now look, we are adding and subtracting inside the expected value function, so we're going to split up the expected value function over that addition and subtraction. The expected value of r squared minus the expected value of, I'm going to write this as 2 mu times r plus the expected value of mu squared. Now, for a random variable, the expected value, or the mean, mu, is some number. It's a constant. So we'll note that 2 times mu is also a constant. And the expected value of mu squared, or sorry, mu squared is also a constant. So because 2 mu is a constant, we're going to pull that outside. And this last one, the expected value of mu squared, because mu squared is a constant, the expected value of mu squared is mu squared. Now, the expected value of r here, that is mu by definition. So now we have the expected value of r squared minus 2 times mu squared plus mu squared. And now just combining like terms, in our last step, we have the expected value of r squared minus mu squared, as desired. All right, one more fact and then an example. If our random variable, if we have a binomial random variable, counts the number of successes, then the variance is really simple to compute. It's just n times p times q. So in example 348, suppose we toss a die 72 times. So again, dice don't have memory. These are independent events. The number of trials is 72. R counts the number of times that 1 appears. That means that the probability of getting a 1, that's our success. Getting a 1 is a success, so that means that P is equal to 1 out of 6. And Q, well, that's equal to 5 out of 6. Then we want to find the variance. Sigma squared is NPQ, so that's 72 times 1 out of 6 times 5 out of 6. And if you calculate that, you should get 10. The variance is 10 here, and they didn't ask for it, but we could do it just because it's so simple. The value of mu, the expected value, or the mean, is just n times p, 72 times 1 out of 6, and that's 12. We would expect a 1 to come up 12 times.